Assalamualaikum and a very good morning to everyone. So today we will continue our the last topic in the chapter 3 regarding on the BJT, which is on the Miller theorem. Okay, so we have discussed about the low frequency response and how the shape in a Bott plot will be. So now we will discuss about Miller theorem, where for Miller theorem we're going to use for the high frequency response. Okay. Alright, so if we can recall back about the Bott plot, okay, we have a Bott plot. Okay, let's say we have a Bott plot, and the shape of our Bott plot will gonna be as such. Alright, so this is at the low frequency response. Okay, FL frequency, low frequency, and this is our high frequency FH, and at the middle here we call this at the mid frequency. Okay, mid frequency, and we have discussed about this mid frequency when we do the AC analysis, where all the capacitances has been short inside your circuit. The coupling capacitor and the bypass capacitor is short, okay, inside the circuit, right? And during the lower frequency, as what we have learned before, okay, we did consider all the capacitances, okay, the coupling capacitance and the bypass capacitance, and from our calculation we can determine which frequency is dominant, okay, which frequency that comes from the capacitance that is dominant, that will be located at this point. All right, so today what we're gonna do, what we're gonna look is on the high frequency range. Okay, about this high frequency range. So we have learned before, okay, where this high frequency, at this high frequency we need to consider, okay, the internal capacitor, okay, the internal transistor, the internal transistor capacitor, okay, and then load capacitances, okay, load capacitances, and also stray capacitances. Okay, and some call these stray capacitances as parasitic capacitance. Okay, parasitic capacitance. So all of these capacitance, okay, all of this capacitance value will then make our gain, okay, this is our gain, our y-axis is gain, okay, it will make our gain becomes lower at high frequency range, okay, at high frequency range. So now let's look at the one of the effect that we call as a Miller effect capacitance, where this Miller effect capacitance can develop at PN junction. So any PN junction will develop this Miller effect capacitance. Okay, so the Miller effect capacitance, okay, at PN junction, especially in an amplifier application, it becomes noticeable. It cannot be negligible. It becomes noticeable between the base collector junction. So if we can recall our BJT, so this is our BJT. We have our base here, collector here, emitter here. So where this Miller effect capacitance happen? So the Miller effect capacitance happens between the base and the collector junction. Okay, between the base and the collector junction, which, if we can recall again, between this base and collector, we have a internal transistor capacitances that is called CBC. Am I right? between the base and emitter junction, there is also internal transistor capacitances that is known as CBE. And between CE terminal junction of the transistor, okay, there is a internal capacitances that is known as CE. So if we look at this CBC, okay, these internal capacitances between the base and the collector, which known as CBC, also will then, okay, this is also called as Miller effect capacitances. Okay, Miller effect capacitance. Okay, where this is only noticeable at high frequency in common emitter BJT amplifier only. Okay, BJT common emitter for the BJT amplifier. Alright, another situation that will make the Miller effect capacitance become noticeable is at the MOSFET amplifier, where at MOSFET amplifier, the configuration of the circuit that make the Miller effect capacitances become noticeable is at common source configuration. So there are only two two types of devices that make the Miller effect capacitances become noticeable. One is at BJT, only at common emitter configuration. So common base, common collector, it will not cause this Miller effect capacitances. Okay, and then next in our MOSFET amplifier, okay, in our MOSFET amplifier, only noticeable at the common source configuration. Okay, and where the junction at is at gain drain junction. So I will not go to this because we are now discussing at the BJT. So please remember, at the BJT, the Miller effect capacitance only happen at the base and the collector junction, which is also at this junction we have internal capacitance that is known as CBC. Okay, CBC. So the Miller capacitance, okay, and it affects, okay, since that it appear at the base and the collector, and if we can recall back from the knowledge of BJT that we have learned, base is our input, this is our input, and collector is our output, right? So therefore, since that there is an effect of Miller capacitances, therefore there is an effect at the input and output circuit. So this is between the input terminal and output terminal of the BJT. Okay. Alright. So now let's say that we have again, okay, let's say that we have an amplifier. So this is our amplifier. Okay, so this is the input terminal, the input junction, and this is the output junction. Okay, alright, so between this input and output, alright, between this input and output, there is an effect of Miller capacitance, and the effect of the Miller capacitance can be labeled as CF, which means this is the feedback capacitance. It calls as feedback capacitance. Okay, it called as a feedback capacitance. Alright, so feedback is usually the effect of the feedback is between the input and the output. So since that we have capacitance, so that's why it is given as a capacitance. So feedback between the input node and the output node of an amplifier. Alright, so at the input node, okay, at the input node, alright, so at the input node, okay, the effect of the capacitance, okay, can be calculated at the input node is known as CMI. Okay, what is CMI? So CMI is the capacitance of the Miller effect at the input node. Okay, CMI is the capacitance of the Miller effect at the input node, and it can be calculated by 1 minus AV, okay, 1 minus AV, multiply with the value of CF. Multiply with the value of CF. So this value of CF, okay, this value of CF is the value of the feedback between the input capacitance, okay, feedback capacitance between the input and the output. And if we can recall back, we always need to relate with the internal capacitance that you have been introduced to. So this is our base, this is our collector, and this is our emitter. So base is our input, okay, base is our input, and collector is our output, right? Between the base and the collector, we have internal capacitance that is called as CBC. As I mentioned earlier, that this CBC, alright, that this CBC also can be mentioned as CF, which is the feedback between the input and the output, alright? And if you look in some books, okay, and if you look some books, this CBC, okay, this CBC is also, okay, is also known as C mu, okay, C mu. So this C mu, CBC, and CF is the same, alright? C mu, CBC, and CF is the same. Whereas between the B and E junction of the BJT is given or is noted as, the capacitance is noted as CBE, right? CBE, base and emitter. However, some books, okay, in some books, they give the sign as C pi. Okay, so when you see C pi or CBE, it is actually the same. Okay, it is actually the same. And CE, capacitance between C and E is given as CCE, and this is not changing lah, because usually it is given in all books it's referred as CCE, collector and emitter. Alright. Okay. Now, alright. Okay. So now, in order for us to calculate the effect of the Miller at the input, okay, let's say now this CF, okay, so this CF now happen between the input node and the output node, okay, between the input and the output, and between this input and this output we can separate it to become CMI and CMO, okay, alright, CMI and CMO, which is capacitance of Miller effect at the input, capacitance of the Miller effect at the output. So how we want to get this value of CMI and this value of CMO? By using this formula, okay, where CMI can be calculated by 1 minus with the value of the gain, okay, value of the gain between the output over input, okay, value of voltage gain, okay, value of voltage gain between output over input, multiply with the value of CF, okay, multiply with the value of CF. Alright, so usually, okay, so let's say let's assume the value of A, sorry, okay, wait, yeah, what happened now? Wait, I need to, alright, so it has some notation there. Wait, how to stop subtitles, okay, alright. So how to what again, how to okay, let's give us some value. Let's say we have an amplifier, okay, so this is our input, Okay, let's say we have an amplifier. This is our input voltage and this is our output voltage, and we have a feedback capacitance here that is known as CF. Okay, so this is also can be redrawn as, we can draw it as, this is the input voltage, this is the amplifier, and this is the output voltage, and we said that this CF can have CMI and CMO, right? So how it can be drawn? So we have CMI here, where it goes to ground, and we have CMO here. Okay, CMI here and this CMO here. Alright, so now let's say we want to get the value. Let's put the value. A now is the what we call as the A is an amplifier, but a negative gain amplifier. It has a negative value of amplifier. Let's assume it to have the value of gain voltage as 100, meaning that the output value is smaller compared to the input value. Okay, so let's say the gain is negative 100. This is only example. Okay, this is only an example, negative 100, and then we want to use this because we want to use this formula. Okay, so now the value of our CMI is 1 minus negative 100 CF. So if we can solve this, we will get 101 almost CF. And so this 101 is approximate to the value of the gain, right? Approximate to the value of this gain again. So we can say actually the input Miller, okay, the Miller effect capacitance at the input is actually how much the value of the gain of the voltage between the output and input multiplied with the value of CF. Okay, I repeat again. Okay, we can say, okay, from this example, we can say the capacitance, Miller effect capacitance at the input value is equal or approximate to the how much value of gain, okay, to how much value of gain multiply with the value of feedback capacitance. Alright, I hope this is clear. So it is actually the capacitance, Miller effect capacitance input is actually how much the voltage gain multiply with the feedback. Alright, so and let's say when you want to solve the question, the value of CF is not given, feedback capacitance is not given. How you want to solve? Actually, you can solve where, because we know this CF is also equals to CBC and is equals to, it equals to C mu. So this value of CF, you can refer to the value of CBC, and also let's say if the value of CBC is not given, if there is a value of mu, then you can also refer to the value of mu. Okay, why? Because of CBC is the internal capacitance between the input and output terminal junction of the BJT. Alright, so that's why we can always refer to CBC or C mu. Okay, because in some books they give us C mu, some books it give us CBC. Alright, okay, I think this formula is very easy, so please remember this formula. Okay, how about the output capacitor? Okay, so remember just now we have the input, this is the input voltage, this is the output voltage, and we have a feedback capacitor which is given as CF, and this is also can be redrawn as such. We have input, we have output, and we have CMI, and we have CMO. Okay, CMI we have calculated just now is equals to 1 minus AV multiplied with this CF. Okay, how about CMO? Okay, so for the CMO, which is the Miller capacitance at the output, okay, the formula is given as such, which is CF multiplied with the voltage gain minus 1 over voltage gain. Alright, so now let's say usually the voltage gain will be much larger than 1. Okay, from what our experience that we have calculated earlier, okay, we can see the voltage gain usually around 200, 100. Okay, so let's say the voltage gain is greater than 1, what will happen? So for example, let's give the value is 200. So now you have 200 minus 1, it will become 199 minus 200. And this is actually almost to the value of, approximate to the value of 200, right? Okay, this is actually approximate because AV minus 1, it doesn't give us any significant value because it just only minus 1. Okay, it will makes us 199 over the same value of 200. So 199 over 200, it almost the same value. So we can say it is actually almost to 1. Okay, same value divided with the same value almost approximately will give us the value of 1. So therefore we can say if the AV is greater than 1, what will happen to the Miller capacitance at the output? It will equals to the value of the feedback capacitance again. Okay, the feedback capacitance again. So therefore it's actually same value with C mu, same value with CBC. Alright, so please remember this formula. This formula is very simple, very easy. Okay, for you to remember, you don't have to derive this, and I also didn't teach you how to derive, so we just straight away go to the formula. Okay, so if the AV is greater than 1, your C capacitance, Miller capacitance at the output will equals to the CF. Alright, okay, and I will always love to repeat, remember that this CF is also known as C mu and also known as CBC. Okay, so same goes to the CF, is also same as C mu, also same as CBC. Alright, I hope this is very clear to you guys. Alright, so these are the, I'm repeating again, I think this is the slide is repeating again. So these are the internal capacitance between the junction of the BJT. We have CBC now, which is between the input of the base, okay, and the output of the collector of the BJT. And then we have internal capacitance that is also known as CBE, which is between the base and the emitter, and also the internal capacitance of CCE, which is between the collector and the emitter. Alright, so for the CBC, for the CBE, okay, if you refer to some books, okay, they didn't mention as CBE, but they mention as C pi. Okay, they mention of as C pi. So C pi is actually same as CBE, alright, and CBC is also in some book refer as C mu. Alright, so please remember this, C mu equals to CBC, C pi equals to CBE. Alright, and all these internal capacitance, okay, all these internal capacitance, usually the value is very small, which is picofarad. Alright, okay, and then at high frequency, what will happen to all of these capacitance? CS, CC and CE, our coupling and our bypass capacitor, it will become short circuit. Okay, it will become short circuit. Okay, because later you need to draw the AC equivalent, so you need to know what happens to all of these other capacitance inside the circuit. So the CS will become short circuit, CC will become short circuit, and CE will become short circuit, same as our AC. But now, what are other capacitance that appear or noticeable is the internal capacitance now, which is C mu, and then what internal capacitance C pi and internal capacitance of CCE. Alright. Not only that, we also have another internal stray capacitance or parasitic capacitance that is known as wiring capacitances, and these wiring capacitances happen at two nodes, at the input node and at the output node. So you have to include this as well in your AC equivalent circuit later, which is at the input node, which is, we know our input is at the base, right? Base is our input. We have a wiring capacitance of CWI. You can see subscript of WI here. W refer to the wiring, I refer to the input, and at the output, which is at the collector, we have CWO, which is W refer to the wiring, O refer to the output. Okay, so now all of this capacitor will be noticeable or will be appear inside your AC equivalent circuit. Alright. So now, okay, so this is the simplified of this is the summarized of CMO and CMI. Okay, so you don't please don't forget about this CMO and CMI. Okay, where is this CMO and this CMI? Okay, CMO and CMI is the Miller effect. Remember, this is actually the Miller effect. And where is this effect happen at? It happen at the input node, which is our base, and output, right, which is our collector. Okay, and this Miller effect is produced from CF, and this CF is actually equals to CBC or C mu, remember? So where is this happen at? It happens at here, this particular part. So this CBC actually, okay, this CBC actually, we can separate it into, okay, let's say we want to draw the hybrid pi model. Okay. I think what is the idea for me to draw? Okay, let's say we want to draw the AC equivalent. Okay, I did have some. Okay, yes, I did have some circuit. Alright, let me add some. We need to keep. Let me add some. Okay, and I need to add this. Wait, yeah, allow me to copy the circuit. Wait, I would like to copy the circuit so that we can refer to this. Yes, okay. And then make it slideshow again. Okay, so now let us draw the AC equivalent now. Let's try to draw the AC equivalent from this. Okay, so the AC equivalent later, it will become, alright, so this CS will become short, CC will become short, CE will become short as well, right? So therefore our AC equivalent will become, this is our VS, alright, goes to ground, and then we have our RS, this is our RS, and then we have R1 and R2 here is parallel, R1 parallel with R2, okay, and then what else we have? We have our wire at the base, okay, so now we go to the base, okay, at the base we have CW, we have CWI, okay, and then between the base and the what here, base and the emitter, we have another base, and then here is our emitter, right? Okay, so base and emitter we have C yes, we have CBE. Okay, and then goes to here, and then what else? We have CBE, and then at the collector, after it goes to emitter, then it will goes to collector. Alright, I forgot about the GMV pi. So we have GMV pi, we still have GMV pi. Okay, so here now is our collector. So let's assume our VA is equals to infinity, so we don't have our R naught. And then at the collector now we have, okay, our emitter, I forgot to mention, our emitter, since that this capacitor is short, so all your current will flow here, so that's why there's no resistor at this part. Okay, next, when it goes to collector, we have RC. We have RC, this is your RC. And then what else? We have, between the collector and the emitter, we have one capacitor here, CCE. We have CCE. Alright, we have CCE. Wait. Let me draw properly, a proper. Let me draw the proper one. Okay, we have CCE. Okay, and then we have another one is RC. This is our RC. And then next, what else? We have CWO. And then next we have RL. Okay, alright. So this is how it gonna looks like. So since that this is, we can also draw it as such, okay, because our emitter is grounded, so we can just connect all this ground here to one ground. Okay, now left only this CBC. So this CBC is actually, I'm using the different color. Okay, I'm using the different color. This CBC is actually happen at this part. CBC, right? CBC. It's actually happen at this, between our base and our collector. We have one capacitor here. Okay, so now if you look at this, if we want to solve our AC equivalent circuit, where we need to calculate the R, the input impedance and the output impedance, and also the input capacitance and the output capacitance, it will be very difficult for us. Okay, because of why? Because of the existence of CBC here. Okay, so now how to make it simplified? We can simplify this CBC by using the Miller effect, because we know what? Our CBC is equals to CF is equals to what? This CF is equals to CMI and CMO. Okay, we know, right? Based on our calculation, this CF can be divided into CMI and CMO, where, if you still remember, okay, I draw it too up. Let me make it down a bit. Okay, this is A, this is our input voltage, this is our output voltage, and this is your CF, right? So this is also equivalent to amplifier. One is, oh my god, because we have a line there. Let me make it to the, okay, like this. This is CMI, and this is CMO. This is V input, V output. Alright, so we can see here our CF we can divide it into CMI and CMO. So same goes to this CBC. We can divide it into CMI and CMO. So therefore we can redraw back our AC equivalent to be as, this is our RS, this is our R1 parallel with R2, okay, resistor again, and this is our base collector junction, okay, which is, this is our CWI, okay, CWI, and then this is our C pi. Remember, C pi and CBE is the same, okay. Next, this is our CMI. Alright, so now you have CMI there, okay. Then it goes to the where? It goes to the emitter, and this emitter is ground because it nothing's have there, okay. Connect all of this. Alright, so this is our, your input will be, okay. Okay, I forgot about the R pi. Okay, so sorry, I forgot about the R pi at the base. So we have R pi 1, yeah. I forgot about that, I'm so sorry. Actually we have R pi here, okay, R pi, and across that we have V pi, right? Okay, so now let's me add R pi here. Let's add the R pi with, I want to add my R pi. Okay, so this is R1 parallel with, sorry, R1, not Ri, parallel with R2, and this is R pi, okay. Alright, so this is our base. Okay, so this is your base. Alright, so we have emitter here. Okay, now goes to the collector junction. We have GMV pi, okay, and then we have RC, and then we have RL, and then we have CWO, and then we have what else? CCE, and then we have CMO, right? Okay, so this is how your equivalent circuit will be. Okay, so if you perhaps maybe some of you ask, the RL should be at the end, why I put it here? Okay, why I put it, I arrange or rearrange back all of this resistor and the capacitor is because it's easier for us. Usually we will put all the resistor at one side, all the capacitor at one side, okay, all the resistor at one side, all the capacitor at one side. So we just put our resistor RC and RL beside to each other, but it is still parallel. Okay, it is still parallel. Okay, we didn't change the configuration type, it's still in parallel connection. Okay, only the position we change because it's easier for us to calculate later what is the value of the impedance and what is the value of the capacitance, because we put all the capacitance in one place and all the resistor in one place. Okay, I hope you understand the how to draw this AC equivalent circuit. All right. Okay, so now if you look here, okay, so this is how your circuit will gonna be. Okay, so I think I have explained earlier, so we can see here, this is your VS, this is your RS, and this RBB is actually R1 parallel with R2, okay, R1 resistor at the base, so that's why they put it as RBB. okay, which is R1 parallel with R2, and then at base we have R pi. Don't forget about that. So since all of this is parallel, okay, RS and then parallel with this, so your R Thevenin, okay, in order for us to calculate the value of the input and impedance, so the input impedance will be your RS parallel with R1 parallel with R2 and parallel with RI, okay, RI, this is not RI, this is actually R pi, I'm sorry. Can you please make it a correction of it, okay? This is supposed to be R pi, okay? So RS, R1, R2 and R pi all is in parallel, okay? Or you can also say that RS, okay, R Thevenin is also RS parallel with Z in, which is this Z in, okay? This is your Z in, yeah? R pi, R1 parallel with R2 and then parallel with R pi. Okay, alright. Okay, so either one is easier. I think this one is easier, okay? Because we can see directly all is in parallel connection. Okay, next C in. Okay, so C in, what is C in? C in is the input capacitance, and how to measure this input capacitance? So this input capacitance is C pi plus CWI, which is the input wiring, plus with the value of CMI. So CMI, how is the value can be calculated? How we want to get the value of CMI? CMI is equals to 1 minus AV CF, or 1 minus AV C mu. Okay, so don't forget about that, right? CF or C mu. Usually all of this value will be given to you. AV value will be given, C mu value will be given, alright? So you just add together, you will get the value of CI. So remember to find the frequency, the formula is 1 over 2 pi RC. So in this case, we want to find the value of the frequency at the input. Okay, so since that this is in high frequency, so usually it is noted as FHI, high frequency input value. So we're gonna be 1 divided with 2 pi R Thevenin, which is R at the input, all of this, okay, all of this R, okay, multiply with the C input, all at the input node. Okay, so CI also can be calculated by using this, okay, alright, CMI, alright. Now let's look how we want to get, or how we want to determine the value of frequency at the higher frequency response at the output node. Okay, at the output node. So at the output node, we still use the value of F equals to 2 pi RC, but remember now our C we're gonna be C at the output. Okay, so C at the output we're gonna be CWO plus CCE and CMO. And remember, CMO can be calculated by using AV minus 1 over AV CF. Alright, so this CF value can be determined from the value of C mu. Alright, okay, and if the value of AV is much greater than 1, so therefore your CMO is equals to CF or C mu. Okay, so it depends, right? And then your R here will be your total R at the output. So since that our RL and RC is parallel, so you have to get the value of RC parallel with RL, and then you just replace inside this formula and you will get the value, you will get the value of frequency at higher response at the output. Okay, right, so I hope that is very clear to you guys. So now let's look into example number 3. So at example number 3, let's look here. Determine the value of high cut-off frequency. So from here we know, we want to get the value of FH for the amplifier circuit shown below. So we have the amplifier circuit down here. The beta is given to us. We have R1, R2, CS, RS, RE, CE, RL, and CC. And given the value of GM is already provided to us, the value of the output wiring is given to us, capacitance wiring input and CCE, C pi, C mu, CBC, and VA is infinity. Alright, so first of all, we need to draw the AC equivalent circuit. Usually the question will ask us to draw the AC equivalent circuit. So how your AC equivalent circuit will gonna looks like? So it will gonna looks as such. Okay, so if we can recall back, all the CS, CC, the coupling capacitor, it will become short circuit, and the bypass capacitance also will become short circuit. So therefore, this will not be included inside your AC equivalent circuit. Alright, next, we need to draw all the capacitances value inside here. Okay, all the capacitance value inside here. So if you look at this AC equivalent circuit, this is not quite complete. It is not included all the capacitance value, right? So let's draw the complete one. Okay, wait, let me minimize this. Okay, I want to wait. Oh yeah, okay, because this is not the, alright. Oh, wait. Okay, Command C, right-ish. Paste it as picture, and make it minimize. So this is your AC equivalent circuit when we solve using the mid frequency. Okay, this is the shape at mid frequency, but we want at the high frequency. Okay, how about the AC at high frequency? So your structure or your circuit will then become RS, VS. Okay, we have RBB. Okay, and then we have and then we have R pi. This is your RBB. Okay, RBB is R1 parallel with R2. Okay, this is your RS, this is your R pi. Okay, and then don't forget we have CWI, input wiring, and then what else we have? C pi or CBE. Okay, and then what else we have? We have CMI. Okay, right, so then finish at our base. Okay, now our emitter, because it is a short circuit there, so it will be no resistor, and then we have GMV pi here. You still need to draw the GMV pi. Okay, and then since our VA is infinity, so there will be no R naught. Okay, and then we have RC, and then we have RL, and then we have CWO, output wiring, and then we have CBC, CCE, and then we have what? CMO. Okay, alright. Okay, so next, so this is how your AC equivalent circuit at the higher frequency. So when they ask, you need to draw this one. Okay, this is your C. Alright, so first, since that the AV is not provided, so you need to get first the output voltage and the input voltage. So output voltage, we know V output is equals to what? Negative GM V pi divided with RC and RL, right? Output RC with RL. Am I right? Okay, and then how about our input voltage? Our input voltage V in is parallel with V pi, so our V in is equals to V pi. Okay, so if we divided both of this, this V pi can be cancelled out, so that's why your AV is equals to GM RC parallel with RL. So you will get negative 60. Okay, you will get negative 60. Alright, so next, what we need to find, okay, we need to find the question as FL, right? FHI and FHO. So FHI, the formula is F equals to 1 over 2 pi RC, where R at the input and C at the input. For FHO also, F over 1 2 pi RC, R at the output and C at the output. So first of all, we need to find the C in. So to get the C in, we know C in is equals to all of the C, right? CWI plus C pi plus CMI. So we need to determine the CMI first. So CMI, by right, I hope by now you already remember the formula CF. And CF is what? It's not given, right? But then what is provided to us? The value is C mu, which is 3 pico. C mu, okay? AV, we can use the value from negative 60, okay? And this is the value from, the value from C mu. So you will get CMI is 183. Next, since that if you want to find the value for the higher frequency at output, we need CMO, because our CO is equals to what? CO is equals to CWO plus CCE plus CMO, right? And this CMO is equals to CF AV minus 1 over AV. Alright, so the value of CF is equals to C mu. Alright, so you can use the value of C mu here. So you will get the value is 3.05 picofarad. So from here you can find the value of CI and R Thevenin. So R Thevenin will be the R1, R2 parallel with R pi and RS. Okay, and you will get the value is such. And you can substitute inside the equation. So you will get the value is 887.239 kilohertz. For the output, you will get the value is R Thevenin is equals to RC over RL at the output, and then CWO, CCE, CMO, you sum up all together, you will get 12.05, and once you get both of that value, you can substitute inside the equation and you will get 11.05. So now you have two value, 887 and 1105 megahertz. Alright, so based from these two value, there are two cut-off frequency value, 859.1111.1111, okay, 0.11 kilohertz, and FHO equals to 11.01 megahertz. Okay, usually the question will ask, what are the cut-off frequency FH that dominates? So to choose the cut-off frequency that dominates, what it means by dominates here is the one that will make a reduction, okay, where your gain will reduce. Okay, so that is what it means by dominates. So usually for cut-off frequency, for higher frequency, it is opposite with lower frequency, where for lower frequency, usually the highest value will be dominates, right? But for higher frequency, the frequency that will be dominates is the lowest cut-off frequency. So between FHI and FHO, you need to choose the lowest, which is our lowest now is 859.11 kilohertz. So this will be our dominates frequency. It means that at this particular frequency, your gain will start to reduce. Okay, your gains will start to reduce. So your answer will gonna be 859.11 kilohertz. Okay, remember the dominate frequency between the higher and the lower is always opposite to each other. For lower frequency, the one that will be dominates is the higher value. Okay, but for higher frequency, the one that will be dominates is the lower value. Okay, you need to choose the lowest value. Alright. Okay, I think that's all. So we finished our BJT topics. Okay, we have covered about the low and high frequency for CE. Okay, and also how to draw the board plot. Okay, so this is how your board plot. I think I forgot to explain about this graph. So this is how your board plot will gonna be. So this will be your the lower value for the highest, from the highest frequency, which is around 859. Okay, 859 kat sini kan, 859.11. And then start from there, it will drops. Okay, it will roll off 20 dB per decade. So now this will gonna be your another frequency, which is 887. Sorry, this one, yeah, 11.01 megahertz. So at 11.01 megahertz, okay, your frequency response, okay, will drop negative 20. Okay, it will drop negative 20 dB per decade. And then from here it will drop again, and this roll off is negative 40 dB per decade. So don't forget to label. Okay, so when you draw your board plot, you just put your lower value. FHI is your lower value, right? Okay, yes. So this is actually equals to 859.11 kilohertz. Okay, and then from here you just make it negative 20, and this is, let's say this is your FHO, which is 11.01 megahertz. Okay, megahertz. So you just show that this will gonna be drop negative 20. Oh, sorry, please draw a proper line. Okay, so this roll off is 20 dB per decade. Okay, negative 20 dB per decade, and then from here it roll off again, but we don't know where it's gonna be stopped, so you just write 40 dB lah, negative 40 dB per decade. Okay, so this is how your structure will gonna looks like. Okay, your sketch graph will gonna looks like, right? Okay, I think by right I will end our class. I will end our lecture. So that's all. If you have any questions, so please don't hesitate to come and ask me. So thank you very much.